The paper title is FineDiving, a fine-grained dataset for procedure-aware action quality assessment. Action quality assessment is a task to assess how well an action is performed by estimating a score after analyzing the performance. As one of the key techniques of understanding sports action, it has attracted growing attention in recent years. Diving events are usually filmed in a similar environment, and all athletes perform the same action routine, that is takeoff, flight, and entry. The subtle differences mainly appear in the takeoff directions, the numbers of both somersault and twist turns, poses as well as the executed qualities. Capturing these subtle differences requires the AQA method to parse the steps of diving action and explicitly quantify the executed qualities of these steps. However, most existing AQA methods regress on the deep features of videos to learn the diverse scores, which would be a confusing and non-transparent assessment of the action quality, since we cannot explain the final score via analyzing the performances of action steps. Considered that existing AQA datasets only contain coarse-grained labels, it is urgent to construct a fine-grained sports video dataset for encouraging a more transparent and reliable scoring approach. The contributions of this work can be summarized as two aspects. First, we construct the first fine-grained sports video dataset for the AQA task, containing rich semantics and temporal structures. Second, we propose a procedure-aware approach for AQA, which learns a new temporal segmentation attention model and quantifies action qualities in a fine-grained way. We first introduce how to construct fine diving. We collect various diving events in Olympics, World Cup, and World Championships on YouTube. Each official video provides rich content, including diving records of all athletes and slow playbacks from different viewpoints. We construct semantic and temporal structures, where each structure contains two-level annotations. The two-level semantic structure contains action types and sub-action types. Action type indicates an action routine described by a dive number. Sub-action type is a component of action type and depicts the types of steps in action procedures. The combination of the sub-action types can produce an action type. In the top right half, the green branch denotes different kinds of takeoffs. The purple, yellow, and red branches respectively represent the somersaults with 3 poses, where each branch contains different numbers of somersault turns. The orange branch indicates different twist turns during somersaults. The light blue denotes entering the water. The statistics in the bottom right corner show the action type distribution and sub-action type distribution. In two-level temporal structure, the first-level labels locate the temporal boundaries of valid action instances. The second-level labels are the starting frames of consecutive steps in action procedures. This is the architecture of our method. Given a pairwise query and exemplar instances with the same action type, we extract spatial temporal visual features with i3D and propose a temporal segmentation attention model to assess the query action quality through procedure segmentation, cross-attention learning, and fine-grained contrastive regression. We formulate the problem as a regression problem, which can be represented as equation 1. In TSA, we first use procedure segmentation to parse action into consecutive steps with consistent semantic and temporal correspondences. Then, we leverage the transformer to learn procedure-aware embedding of query and exemplar steps. Finally, we perform fine-grained contrastive regression on the procedure-aware embeddings, which quantify stepwise quality differences between query and exemplar, and predict action quality score. During training, the objective function can be written as equation 2. We adopt a multi-exemplar voting strategy during testing. In experiments, we compute 3 metrics to comprehensively evaluate our approach. Table 2 shows the experimental results of our approach and other AQA methods. Our approach achieves the state-of-the-art. In Table 3, we conducted more analysis experiments for studying the effects of different components. Besides, in Table 4, we conducted some experiments to study the impact of M on our approach. Table 5 investigates the effects of the number of frames in each step on the performance of action quality assessment. Table 6 explores the effect of the number of transformer decoder layers on the performance of action quality assessment. In the visualization, we see that our approach can focus on the exemplar regions that are consistent with the query step, which makes stepwise quality differences quantifying reliable.